We're going to do a review now of some basic integration formulas. Some of these come straight from their derivatives. Some of them we're going to need to do a little bit of work like a substitution, but by the end of this, you're going to recognize that you need to commit these to memory, and they'll be very, very useful to you as we proceed in learning a variety of other integration techniques. Our first two don't need any work to figure them out. The antiderivative of a constant k dx is just k times x plus our integration constant, and then the antiderivative of x raised to the p power, where p is any number except for -1, as long as it's a real number. We know we're going to add 1 to our exponent and then divide by the new exponent, and of course we need our constant of integration there as well. This next one's pretty straightforward. We just need to recall that the derivative of the sine x function is cosine of x. So that tells us that the derivative or the antiderivative of cosine must be sine. But of course we have the addition of an a in here. So if we look at the antiderivative of the cosine of ax dx, we can do a very simple u substitution, letting u be ax, so that du is a dx, which means that 1 over a du must be dx, so that our integral becomes 1 over a times the integral of the cosine of u du. That is just going to be sine of u plus a constant. And so we see that we do in fact get 1 over a times the sine of ax plus a constant. Hopefully based on that one, it'll follow pretty quickly that the antiderivative of sine ax is going to be similar. So again, we're going to remember here that the derivative of cosine of x is negative sine x, which means that the antiderivative of sine x must be negative cosine x plus c. And then we have the addition of our a here, so we're going to do the exact same trick we did before. We'll let u be ax. That's going to make 1 over a times du equal to dx. We end up with 1 over a times the antiderivative of sine of u du, which is 1 over a times the negative cosine of ax plus our constant c. These next four all follow again from a very similar substitution as well as their corresponding derivatives. So it's sufficient for us to remember here that the derivative of tangent of x is equal to secant squared of x. The derivative of cotangent of x is negative cosecant squared of x. The derivative of secant of x is secant x tangent x, and the derivative of cosecant of x is negative cosecant x cotangent x. All of those derivatives combined with a simple substitution will result in the formulas you see here. Not a lot new going on with this one. We'll remember here that the derivative of e to the x is itself, which of course then means that the antiderivative of e to the x dx is e to the x plus c. So when we want to look at e to the a times x, we're going to do a substitution. U will be a times x, du will be a dx. So 1 over a du replaces dx, and we end up with 1 over a times the antiderivative of e to the u du, which by the above is 1 over a times e to the u plus c, and we get 1 over a e to the a times x plus our constant c. All right, our next formula gives us an antiderivative for things of the form dx over a plus x or 1 over a plus x. What we're utilizing here is that the derivative of the natural log of x is equal to 1 over x. which then tells us that the antiderivative of 1 over x dx is going to be the natural log of x. We need the absolute value here because it's possible in our antiderivative that x could be a negative number, but we can't take the natural log of a negative number, so we put the absolute values on it to take care of that. Put in our plus c. So now when we have 1 over a plus x, or if we have dx over a plus x, we're again going to do a simple substitution. U is a plus x. Since a is a constant, its derivative is 0, so we get that du is dx. And this just becomes the antiderivative of du over u, which is what we have above, and that is going to be the natural log of the absolute value of u plus c, which becomes the natural log of the absolute value of a plus x plus a constant c. Our next couple are maybe slightly less trivial than some of the ones we've looked at here. So now we have the antiderivative of dx over x squared plus a squared. So what we're going to use in order to do this is we're going to remember that the derivative of the arctangent function of x is 1 over 1 plus x squared. So that tells us that if we were to antidifferentiate 1 over 1 plus x squared, we would just get the arctangent of x plus a constant. We now want to look at 1 over some other number squared, a squared plus x squared dx. In this case, letting u be a squared plus x squared isn't really going to work, because notice then that du is 2x dx. That doesn't work. We have to do a little bit of algebra. Okay, so what we're going to do is we're going to factor out an a squared in the denominator. So I'm going to rewrite the denominator as a squared times 1 plus x squared over a squared. Notice that that is 1 over a squared times 1 plus the quantity x over a squared. We can pull the 1 over a squared out in front, so we'll get 1 over a squared, and then we have the antiderivative of 1 over 1 plus x over a squared dx. Now we can do our u substitution. We can now let u be x over a, so that du becomes 1 over a dx, which then tells us that a times du is equal to dx. Now, if we plug that back in, we end up with 1 over a squared, and then we have the antiderivative of a du over 1 plus u squared. We'll move the a that's on the inside to the outside, which gives us 1 over a. Now we have the antiderivative of 1 or of du over 1 plus u squared, which, given what we started with, we know is 1 over a times the arctangent of u plus a constant, which gives us 1 over a times the arctangent of x over a plus our constant c. We're going to use very similar techniques for this one. So we're going to recall here that the derivative of the arcsin function is 1 over the square root of 1 minus x squared. So reversing that process gives us that the antiderivative of dx over the square root of 1 minus x squared is going to be arcsine of x plus a constant. Now we'll look at what happens when we throw a number other than 1 in that square root. So again, we'll see a substitution is not going to work for us because we end up with a 2x in our derivative, which we don't have anything to replace. But we can do the same thing we did for the previous one. We can divide out an a squared. So under my square root, I'll have a squared times 1 minus x over a all squared. I can split that up. That's the square root of a squared times the square root of 1 minus x over a squared. We're going to assume here that a is a positive number so that when I take the square root of a squared, I get a back again. That won't happen if a is negative. So our assumption here is that we're looking at the positive number a. So we have now dx over a times the square root of 1 minus x over a squared. Now we get 1 over a times dx over the square root of 1 minus x over a squared. So after all that algebra, we're ready to do our substitution of u equals x over a, so that du is dx over a, or a times du is equal to dx. And if you were wondering why there was no 1 over a in this one, here's why. When we replace dx with a du, we can bring the a out front and we have a over a, which is just 1, and then du over the square root of 1 minus u squared, which just becomes the arcsine of u plus a constant, which is the arcsine back substituting of x over a plus a constant. This next one relies on the same exact techniques as before, factoring out the a squared from the bottom, and then we rely on our memory to remind us that the derivative of the arcsecant function is 1 over the absolute value of x times the square root of x squared minus 1, and reversing that, combining it with our factoring out of a squared and our u substitution, we'll get this formula for us. We'll need some different techniques for this one. We don't have a function whose derivative is tangent, so we can't very easily anti-differentiate this, but what we can do is use the fact that tangent of x is the same thing as the sine of x over the cosine of x. And if we remember that, then the antiderivative of the tangent of x dx becomes the same thing as the antiderivative of sine x over cosine x dx. And notice here that sine is the negative derivative of cosine, so we can do a u substitution. We can let u be our denominator, cosine x, so that du is then negative sine x dx. And we can rewrite this integral now as negative integral of du over u. That's one we saw just a few minutes ago. That's a natural log. So we get, this is the negative natural log of the absolute value of u plus some constant, which is the negative natural log of the absolute value of the cosine of x plus a constant c. When we add in an ax, now we have the antiderivative of tangent of ax dx. Well, now we're going to do another u substitution. We're going to let u be ax, so that du is a dx. So 1 over a du is dx. Hopefully have committed this type of substitution to memory by now and won't need to write it all out in detail as you move through these. So this becomes 1 over a times the antiderivative of the tangent of u du. And that gives us, using what we did above, negative 1 over a times the natural log of the absolute value of the cosine of u plus c. And replacing u with our x's, we get negative 1 over a times the natural log of the absolute value of the cosine of ax plus our constant c. The next one here just relies on the fact that cotangent is equal to cosine x over sine x, and then would proceed with the two same substitutions, or very, very similar substitutions to what we used to derive the antiderivative of tangent of ax, so I won't work out the details here. This next one actually requires probably the most sophisticated algebraic tool that we've used so far. It's going to rely on a couple of facts, the first of which is that the derivative of secant of x is secant x tangent x, and that the derivative of tangent of x is secant squared of x. Now, it might not be immediately obvious how that's helpful, but what we're going to do is, if we look at the antiderivative of secant x dx, what we're going to do is multiply our integrand by a form of 1, and we're going to choose that form of 1 to be the function secant of x plus tangent of x over secant of x plus tangent of x. The reason that's helpful is because when we distribute our secant x, we get secant squared of x plus secant x tangent x all over secant of x plus tangent of x dx. And we know that this is the derivative of tangent of x, and this is the derivative of secant of x, so that if we let u be our denominator, secant of x plus tangent of x, then du becomes secant x tangent x plus secant squared of x dx, which is our numerator. It's written in the reverse order, but it's all commutative. So we end up with du over u. And that is going to be the natural log of the absolute value of u, which in this case is the natural log of the absolute value of secant of x plus tangent of x. Now, of course, we need to account for the fact that we started off with an a, but that's going to be our very familiar substitution. So we have the secant of ax dx. We just let u be ax, du is then a dx, and we end up with 1 over a times the antiderivative of secant of u du, which becomes the natural log of the absolute value of secant u, which is ax, plus tangent u, which is again ax, plus a constant c. And for our grand finale, we'll take a look at the antiderivative of cosecant of ax. This is going to rely on the fact that the derivative of cosecant of x is negative cosecant x cotangent x, and the derivative of cotangent is negative cosecant squared of x. Utilizing those, plus the exact same technique we used in the previous example, both the multiplication by 1 and then the eventual u substitution of ax will lead us to the formula that we see here. To wrap this up, we've got a summary of all 17 of the formulas we've seen throughout this video.